Okay, so I'm going to just review the end of last Wednesday's lecture. So we started talking about the size principle of recruitment. You'll note that there is an exam question on order of recruitment. We will, in another lecture, get to more details about order of recruitment, but this is just introductory size principle, right? And here we know that the smaller fiber motor units are recruited first before the larger ones. We talked about muscle tone and that muscles are always in a constant state of contraction, and they're alternating which ones are so that they don't fatigue, but this allows them to be primed and ready for action, willful action, or for example, reflex. Well, we mentioned hypotonia, lack of tone, and hypertonia, more tone. The atrophy is the wasting away of any muscle, and we have two types here. We have disuse because we don't use the muscle, and we have degenerative because the brain can't communicate to the muscle. Hypertrophy is the opposite. It's just an increase in size. Hypertrophy is an increase of the muscle tissue fibers, and that you can do with exercise, for example. Hyperplasia is different. It's when there's a different mass other than skeletal muscle tissue in that area. So that would be an abnormal occurrence, although common. And then also that this would then decrease the function of the skeletal muscle. Oh, I want to go on slideshow. Here we go. Okay, so now something new. So this is where we're kind of kicking off for today: isotonic and isometric contractions. So an isotonic contraction, we have that word tone or tonic again, right? And iso means it remains the same. So the muscle changes in length and moves the load, but once the load is moved, it maintains that muscular contraction force. They can be concentric or eccentric. Concentric contraction muscles is when the muscle gets shorter as you contract, and eccentric, the muscle lengthens. So let me go get a heavy book and show you how this works. Okay, so here's my heavy book. So when I go, this is my table. Hang on, let's get set up here. So I go to pick this heavy book off of the table, and oh, my lighting is terrible, guys. Well, here we go. Okay, here's my book. I want to show you my bicep contraction. So when I go to contract the muscle or lift it up off the table, I'll explain it with my fingers. So when the muscles shorten, right, it causes the contraction and they get shorter. That's a concentric. Eccentric is if I'm lowering something down, my muscle actually gets longer as I lower it down towards the floor. I totally botched that. But laying a book down causes biceps to lengthen while generating a force. So you can just do that, right? So like this is concentric, the bicep muscle shortens. Then if I'm laying that same book down on the table, my bicep muscle actually gets longer because of the force of the book in my hand, the weight, the load. There's a tension on it, and that's why there's an eccentric contraction. Thanks for waiting. Okay, so this is
here's a look at that. So here,
this is hang on. Okay, we're just gonna keep going because this is how I end up losing content, is that I re-record and there's not enough hours in the day to re-record these things all the time. Okay, so isotonic contraction. So here we see that this is the load of the book. Then as I contract my bicep muscle shortens and the load gets lifted. It's isotonic because now that I'm holding that book, right, in that place now, these muscles remain contracted until something happens. So the book moves, I put it down, whatever. But the tension remains. That's why it makes it isotonic. It's the same force of tension along. It's also true that the amount of tension from initiation of movement to the end of the movement is the same. It just gets displaced a little different. So that's also another reason why it's isotonic. In graph form, this is what it looks like. So we have the tension, the developing, we have the peak tension developed, So this becomes our isotonic contraction. There, let's look at the length, right? When the stimulus is here, it's at like 100 if for the resting length, but when time goes and we start to contract, the length gets shorter and shorter and shorter. That's why this dips down, and then it remains until you offload the load. And you could maintain a contracted bicep, offload the load, and still keep the length shortened as well. So that's a possibility. Go back to slideshow form. Okay, so isometric. So we just talked about isotonic. Now isometric is when the load is so great that there's no change, there's no work, right? Work equals force times distance, right? Force over distance is the amount of work. So if there's no change, then there's no distance moving, then the work is equal to the force, but there's no movement. So it's technically not work because there's no movement. Although you would be contracting your muscles to make it work. So in that sense, there's energy generation. I love this. So this is what happens. This is an isometric contraction here with this guy. He's going to school and he's pushing on the door. And it's not going to open because but he's going to generate force and have an isometric contraction. It neither shortens or lengthens. So this could also be when you're lifting something that's too heavy. You want to try to lift it, but there's no motion. That's an isometric contraction. Isometric contractions are also in position, holding weight, and no movement. You then maintain an isometric contraction, right? You might do an isotonic concentric contraction to get there, but then remaining here engaged is an isometric contraction. What else? Electrochemical and mechanical events are same in these. So what's happening at the microscopic level is the same, but the results are different. So the actin filament shortens and causes the movement in the isotonic contraction. In the isometric, the cross bridges generate the force, but the actin filaments don't actually move. So the cross bridging, which is that myosin globular head moving, it keeps moving, which we call spinning on the wheels, but it doesn't cause the actin filament to shorten, but it generates that power, that force, or that contraction in that way. So that's an isometric contraction versus an isotonic when the actin filament shortens, which is really where we looked at muscle contraction when we started, right? We were looking at isotonic contractions. Here's another graph of isometric, right? And this is simply illustrating that there's a peak tension developed with the amount of resistance, and that happens over time. What doesn't change over time is the resting length. Okay, so you can start to generate. Guys, you're so forgiving. I appreciate it. So what changes over time is is not the resting length, even though you can continue, you can generate an isometric force slowly, right? More force, more force, more force, more force, and then you're pushing harder and harder and generating. So the amount of tension developed can increase, even though the resting length of that muscle doesn't. This is what it looks like, right? Resting length just doesn't change. Right? I'm pushing on a wall that's not going to move. Nothing changes. Okay, let's pause here. I'm going to stop the recording. Thank you guys so much for bearing with me on that one. Let's let the next one be even more.